Hello guys, welcome to the knowledge domain, the concept of life sciences and biotechnology. In this lecture series, we are going to learn the cardiovascular system. So in this one, we are discussing in this lecture the circuit of the cardiovascular system, that the blood volume contained in the arteries are called the stress volume. So before going into the exact schematic, the stress volume means when it is in the artery that actually takes the blood away from the heart are known as arteries, and the blood present in the arteries are called the stress volume. And in this slide, we will see that the movement of the blood through the blood vessels are the arteries, arterioles, capillaries, where the exchange of the nutrients and the gases takes place between the blood and the tissues. Then the blood is drained from the tissues by the veins finally reaches the heart. So this is the right part of the heart. So vena cava pour the blood into the right atrium, then through the tricuspid valve, it reaches to the right ventricle, and from the semilunar valve, by the pulmonary artery, the blood comes to the lungs for the oxygenation, and the oxygenated blood through the pulmonary vein reaches to the left atrium, and from here to the bicuspid valve, which reaches to the left ventricle, and the muscles of the heart is very thick in this case, and it pumps into the systemic aorta to flood the cells of the body. Okay, this is the circuit and this is the blood vessels names. And the blood present in the arteries are called the stress volume because they are in the stress. And arterioles are the site of the highest resistance in the cardiovascular system. And in case of the arteries, the receptors are the alpha-1 adrenergic receptors that is found on the skin, splanchnic and the renal circulation, and the beta-2 adrenergic receptors that are found in the arterioles of the skeletal muscles. Okay, and in case of the venules that contain the highest proportion of the blood because they have the larger volume in the cardiovascular system. And here the blood is called the unstressed volume because it is very relaxed and the wall is thin in case of the vein and the capacitance is high that we will discuss in this lecture. And here there is only alpha-1 adrenergic receptor is found. So capillaries, where the exchange of the gases and the nutrient takes place between the blood and the tissues, consist of a single layer of endothelial cells that we have already discussed in the two lecture series. One is eukaryotic cell that deals with some tissues, and the another is the cell junctions. So what are the type of the tissues? So this is epithelial cell type, endothelial cell. So this type of cell they need a basement membrane, that is the basal lamina. And when there is a blood vessel, the various layers of the blood present in this vessel, they move in a different speed or the velocity. So the blood that is close, the layer of the blood that is close to the wall of the artery, it is the slowest, and that is at the center of the lumen is the fastest. That is because there is a shear force, means which is close to the wall, so the blood velocity is less there. So velocity of the blood is the Q by A. So V is the velocity, the rate at which the blood flow, and Q is the blood flow, means it is cardiac output, and A is the cross-sectional area of the blood vessels. So this Q means cardiac output or the blood flow is equal to change in the pressure, means the difference in the pressure divided by the resistance. So mean arterial pressure minus the right arterial pressure by total peripheral resistance. So that is the cardiac output. And this is resistance here, that is still unknown, that is 8 eta L by pi R4. So eta is the viscosity of the blood, L is the length of the blood vessels, and the R is the radius of the blood vessels, and this R is this resistance. So in this formula, we know that the blood velocity is the Q by A. Q is the cardiac output or the blood flow. Okay, and this Q equal to difference in the pressure by resistance, and this resistance is A theta L by pi R4. So when the blood is coming from the systemic circulation, it is supplying blood to the brain, to the heart, muscles, to the kidney, to the liver. So this is the organs are present in the parallel arrangement. In this case, the resistance is less. So 1 by R total equal to 1 by R of the each of the organ. But when the blood is coming from the gastrointestinal tract to the hepatic portal system, then to the liver, then to the heart. It means they are in the series arrangement. Or another example is the blood that is draining from the lower extremities of the body that is coming to the renal portal system, and then after that it is coming to the heart. So that is also a series arrangement. In this case, the resistance is the highest. So capacitance or the compliance is the distensibility of the blood vessels. So the larger the capacitance, the blood vessels have the ability to distance. It has the ability to swell forward. That is the capacitance. And it is inversely related to the elastance or the stiffness. So if it is more stiffer, it has less capacitance. So amount of elastic tissue is directly proportional to the elastance. The C for the capacitance or the compliance, that is ml per meter mercury, equal to volume by pressure. So in case of the vein, the capacitance is high, so they can keep a larger volume of the blood. So more blood volume is contained in the vein on stressed volume because they have the higher capacitance. And it is more than the arteries, which has the stress volume. So arteries have the less capacitance, they have the more stiffness because the wall is thicker. And when the people age, also the capacitance of the vein it reduces. So the ability of the vein wall to disten also reduces. Okay. So these are the main pressure of the systemic circulation, like the aorta that is immediately collecting the blood from the left ventricle at a 100 millimeter mercury, arteriole, the highest resistance that has a 50 millimeter mercury, capillary is 20 millimeter mercury, and the vena cava that pours the blood into the right atrium is the 4 millimeter mercury. Okay, so this is a graph. In this we will see when the heart is pumping, the pressure it is generating in the aorta and the heart muscle itself. So when it is contracting at the peak, it is called the systolic pressure. It is almost 120 millimeter mercury. And when it is relaxing, the pressure is the lowest, that is almost 80 millimeter mercury, that is the diastolic pressure. And the pressure in between systolic and diastolic pressure is known as pulse pressure. And this is the arterial pressure. So pulse pressure is the difference between the systolic and the diastolic pressure. That is the pulse pressure. So here we know that aorta pressure and the systolic pressure is 120 and the diastolic is 80 millimeter mercury. Okay, mean arterial pressure is the average of arterial pressure with respect to time. So can be calculated approximately diastolic pressure plus 1/3 of the pulse pressure. So diastolic pressure is almost 80 millimeter mercury, and the pulse pressure, the average of this pulse pressure by 1/3. So pulse is 120 minus 80 equal to 40. So it is almost 13 millimeter mercury. So 80 plus 13 equal to 93 is almost mean arterial pressure. So this is a signature of the electrophysiology of ventricle of the heart. Here you see P, it is a P wave, then you see there is a Q wave, R, S, and there is a T wave. So when the ventricular contract, the arterial contraction started, we can see this refers to the arterial contraction, and this is possible because the arterial muscles they depolarize, and because of that there is a contraction of the atrium. Because of that there is a pouring of the arterial blood into the ventricle. But when this atrium it relaxes, actually this is hidden because of this ventricular contraction. So we cannot see the repolarization of the atrium here. So this is the depolarization. So it is towards the positive, and this is the hyperpolarization, the repolarization. This is towards the negative. Okay. So from the P to the Q, this is the initial depolarization of the ventricle. Okay, and this is the conduction velocity to the atrioventricular node. And this QRS, so from the P to the Q, this is the initial depolarization lead to the means sudden influx of the ions into the heart muscle, so that there will be the sudden contraction. So QRS is the ventricular contraction, and because of this, we cannot see the repolarization of the atrium. It is hidden inside it. And this from the S to the T, this is the repolarization of the ventricle. Okay. So this is the QT, whatever we see here, that is the depolarization, the repolarization, and ST, this is the depolarized state of the ventricle. So here this PR, so this is the time when the atrium is contracting, and this is the time when the impulse of the heart contraction that is initiated at the SA node is moving toward the ventricle to contract it. So this time gap determines, that gives us the information about the transfer of the impulse from the SA node to the AV node. So the PR is sympathetic nervous system, it decreases, means SA node, the firing, when this length decreases, the firing length increases. And parasympathetic nervous system, it increases this time, means the time between the P and the Q, or the PR. So this time is increased by the parasympathetic nerve, means it takes a longer time to the heart to contract, whereas for the sympathetic, it takes a shorter time. This is the cardiac action potential. So action potential is the signature of the depolarization of the heart muscles or any tissues over a fixed period of time. In this case, it is 300 milliseconds. So the resting membrane potential of the ventricle or the Purkinje system muscle is almost around minus 90 millivolt. And here, whatever potassium that is effluxed from the muscles to the extracellular environment, similar amount of potassium they also enter into the cell. So there is a potassium ion equilibrium, and it is almost minus 90 millivolt. Okay. So when we superimpose this action potential of the ventricular muscle, we can see that there is a sudden loss of the sodium to the voltage gated sodium channel, because of there is a increase in the intracellular positive ions. Because of that, there is a depolarization. It reaches to the plus 20 millivolt. Okay, this is the phase one of the contraction. Then we can see there is a small decrease or the small repolarization. This is possible because the sodium influx is completed, and now there is no more sodium influx. But when the sodium cross into the intracellular environment, that is increasing the positivity of the intracellular environment, is means almost going to zero. There is a calcium influx into the cytoplasm to increase this positive charge. Because of that, we can see there is a plateau. So this is the current because of the calcium, and calcium maintains this plateau. And when the calcium released into the cytoplasm from the endoplasmic reticulum, mostly sometimes it is from the extracellular environment, it is finished, then there is the efflux of the potassium from the cell into the extracellular environment. Because of that, if the proton is coming outside, then there is the repolarization. So anyway, the proton is coming outside because of the potassium. So there is a repolarization. So that is again becoming to the minus 90 millivolt. So to summarize it further, sodium is rushing in, positive charges inside is increasing because of the fast sodium channel. So it is suddenly rise. Then this rush of the sodium decreases. So there is a small decrease, but this will be compensated by the influx of the calcium here, plus charge. So again, the positive charge is coming here because of the calcium. So this deep inside positivity is maintained for a small time. So this is the plateau possible because of the calcium influx. Then when the calcium influx also completed, then the positivity is going from here to here. So the repolarization is happening because of the influx of the potassium. So the sodium and the calcium by the voltage gated means channels, whereas the potassium is by the open potassium channel. So there are four phases. Phase one, sodium influx. Okay. Phase two, calcium influx. Phase three, this is the potassium, and the phase four is the potassium equilibrium. So this is the potassium influx. So sodium calcium influx because of that positivity increases and the potassium influx. So positivity decreases from the intercellular environment. Okay. So this is the sinoarterial node action potential. Here this is the phase 4. This is because of the sodium influx. So from almost minus 70 millivolt it is slightly increasing to almost minus 50 millivolt. And here this calcium are the voltage activity. There is a sudden influx of the calcium. Because of that we see the plateau. So there is a phase 0 phase. And in this one, SA node, there is no phase 1 or the phase 2, and there is a phase 3 because of the potassium influx. So this is the phase 4, means how the conductance is taken by the SA node. This is dependent on that. So AV node and this SA node is a pacemaker. So AV node and the Purkinje fiber are the latent pacemaker. Automaticity and they have the property of the automaticity. They override the SA node if the SA node is suppressed. So when the SA node is not working, if AV node can take care of the initiation of the ventricular contraction. So the phase 4 depolarization, that what we see here, it is the highest in case of the SA node and then AV node, and it is the lowest in case of the Purkinje fibers. Okay, then that cardiac impulse transmission, whatever we discussed earlier. So if you see the time kinetics here, this is the 0 second where the contraction of the depolarization of the SA node initiated. Then around 0.03 second it reaches the AV node, and it takes almost 0.09 second to reaches all the muscles of the atrium. Okay, so they will pour the entire blood present here in 0.09 second. But this 0.03, wherever AV node is getting the signal, it is able to transmit the signal to the ventricular muscles. It takes 0.16 seconds. So there is a 0.13 time gap between these. So 0.16 second is higher than 0.09. So when the signal reaches to the ventricular wall, all the blood already they are pumped into the ventricle. So what makes this delayed? So this delay is possible because of this AV node. It takes almost 0.09 second, and the bundle of the keys means that one will discuss in this slide, that take another 0.04 seconds. So they delayed total 0.13 seconds, and around 0.22 second intraventricle contracted to pump the blood into the pulmonary and the systemic aorta. So whatever we have discussed in the previous slide, one of the slides is PR. This is this PR, means SA node, the signal heart contraction initiated here, it reaches to the AV node, and from the AV node to the ventricular wall, it is 0.13 seconds delay. So if the delay will increase, this PR will increase, and if the delay will shorten, this PR will shorten. So this PR determines the ventricular contraction here and the atrium contraction here. So this PR determines this time gap between the SA contraction and the ventricular contraction. So this is the delay. So this is the atrioventricular fibrous tissue, and this penetrating portion of the AV bundle, it takes 0.04 seconds. And in this AV node, it is 0.09 seconds. So where there is a delay in the transfer of the information, because there is a diminished number of the gap junctions in the AV node and this penetrating portions of the AV bundle. So there is a diminished number of the gap junctions. Because of that, there is the slowed transfer of the impulse between the cells in this area. That's why there is a delay of the 0.13 seconds. Then this is the ARP, is the absolute refractory period. This is the ERP, effective refractory period. You can see the ERP is slightly longer than the absolute refractory period. And this RRP is the relative refractory period. And this signifies that means how long this is. This is total 300 milliseconds. Okay. So here we see that effective refractive period, conducted action potential cannot be elicited during this time. And during this time, no action potential can be initiated. Mean during this time, there is no action potential can be initiated. Whereas in this time, RRP, action potential can be elicited, but more than usual inward current is required. So this is the time action potential is initiated. This means that when there is a one action potential already ongoing, that means another action potential cannot be fired. This is because we have already discussed the conductance of the ions. When there is a loss, means as long as it is not repolarized, they cannot activate it to transport the ions across the membrane. This is because of this. So during the ERP and the ERP, action potential cannot be fired. So there is a delay of the time. After that, there can be another action potential initiated. So how it is means control the rate of the heartbeat by the sympathetic and the parasympathetic nervous system. And chronotropic effect is the heart rate, SA node firing rate. Okay, that we will discuss in this slide. And dromotropic effect, the change in the AP node conduction velocity. So one is the rate of firing, that is chronotropic, and dromotropic is the changes in the conduction velocity. Okay, so here is the vagal. Vagal is the parasympathetic. You can see here it is innervating the atrium as well as the SC node and the AV node, but the nerve from the vagus, it is not innervating the ventricle. And the auricle and the ventricle is innervated by the sympathetic chain. So the parasympathetic does not innervate the ventricle. So this ventricular smooth muscle, you don't see there is no parasympathetic signal here. So this parasympathetic signal that is found in here, that is innervating, this is muscarinic receptor. What is the sympathetic? This is adrenergic receptor. So adrenergic has a signal norepinephrine, and the muscarinic receptor has the agonist is the acetylcholine or the ligand. Okay. So parasympathetic vagal, that is innervating the SC node and the AV node, it decreases the heart rate. How it will decrease the rate? By negative chronotropic effect and the negative dromotropic effect. For the sympathetic, they will increase the heart rate by how? It is positive chronotropic effect and the positive dromotropic effect.